Imagine you are looking at the entire universe, not just the stars or the galaxies, but the very fabric of space itself. For a long time, we assumed space was just an empty box where things happened. But one of the most shocking discoveries in the history of science is that space isn't just a container, it has a shape, and that shape is flat. Now, before you think I've joined a flat Earth society, let's be clear, we are talking about geometry, not shape. In cosmology, saying the universe is flat doesn't mean it's a two-dimensional pancake floating in a void. It means that if you draw a triangle across billions of light years, the angles will add up to exactly 180 degrees. It means parallel lines will stay parallel forever, never crossing and never drifting apart. This might sound boring, it's the stuff you learned in high school math, but on a cosmic scale, it is absolutely terrifying. Why? Because the universe had every reason to be curved, warped, or twisted, yet it chose to be perfectly level. Ask yourself this: why would a universe born from a chaotic, hot, and dense explosion end up with the precision of a perfectly drafted blueprint? When we look at the night sky, we see thousands of stars and billions of galaxies all held together by gravity. Gravity is the ultimate shaper of reality. It curves space and time. Einstein showed us that matter tells space how to curve, and space tells matter how to move. We see this curvature around black holes, where the gravity is so intense that space is warped into an infinitely deep well. If matter causes space to curve and the universe is filled with hundreds of billions of galaxies, why doesn't the entire universe look like a crumpled sheet of paper? Instead, when we measure the largest possible scales, the curvature disappears. This is what we call the flatness problem. It's a mystery that forced us to rethink the first fraction of a second of existence. To understand why this is weird, we have to look at the three possible ways the universe could have been built. Think of it like this: if you were a cosmic architect, you'd have three choices for the geometry of your creation. The first is closed geometry. Imagine the surface of a ball. If you start walking in one direction, you eventually end up back where you started. In a closed universe, if you shine two parallel flashlights, the beams would eventually curve toward each other and cross. The second is open geometry. This is shaped like a saddle. In this universe, parallel lines would gradually drift away from each other, and the angles of a triangle would add up to less than 180 degrees. The third choice is flat geometry, or Euclidean geometry. This is the Goldilocks version. It's the only one where parallel lines stay parallel, and triangles behave exactly as they do on a flat piece of paper. Our observations show that we live in the Goldilocks version. But for this to happen, the balance of energy and matter in the early universe had to be fine-tuned to a degree that defies all logic. Why is flatness so unlikely? It all comes down to a battle between two massive forces: the expansion of the universe and the pull of gravity. Astronomers describe this balance using a number called omega. Omega is the ratio of the actual density of matter and energy in the universe to the critical density needed to stop the expansion. If the universe has too much stuff, if the density is high, gravity wins. The universe becomes closed, space curves in on itself, and the expansion eventually stops and reverses into a big crunch. If there isn't enough stuff, if the density is low, expansion wins. The universe becomes open. Space curves outward like a saddle, and everything flies apart forever. But if the density is exactly at the critical level, the universe is flat. It keeps expanding, but at a rate that stays perfectly balanced forever. Here is where it gets weird. This balance is incredibly unstable. Imagine trying to balance a pencil on its tip. If it's perfectly vertical, it stays. But if it's even a hair off to one side, the gravity of the Earth pulls it more in that direction, and it falls over faster and faster. The geometry of the universe works the same way. If the early universe had been even slightly too dense, the curvature would have grown and grown until the universe collapsed within seconds of the Big Bang. If it had been slightly too thin, it would have expanded so fast that stars and galaxies could never have formed. For us to see a universe that is even remotely flat today, it had to be almost perfectly flat at the beginning. We are talking about a precision of 1 part in 10 taken to the 60th power. That is like throwing a dart from across the galaxy and hitting a bullseye the size of an atom. Think about the scale of that number. If the density of the universe just 1 second after the Big Bang had been different by 1/10,000,000,000th of 1%, we wouldn't be here to talk about it. The universe would have either crushed itself into a point or thinned out into a cold, dark void before the first atom could even form. This level of precision is what we call fine-tuning, and it's one of the biggest reasons why physicists believe there is a deeper layer to reality that we haven't fully grasped yet. The fact that we see a flat universe isn't just a lucky break, it's a signature of a massive event that happened at the dawn of time. We used to think the universe was just a static, unchanging background, but now we know it is a dynamic system that was smoothed out by a force we are only beginning to understand. How do we actually prove the universe is flat? We can't exactly take a giant ruler and measure space across billions of light years, but we do have something better, the Cosmic Microwave Background, CMB. This is the leftover heat from the Big Bang, a faint glow of microwave radiation that fills every inch of the sky. When we look at the CMB, we are essentially looking at a photograph of the universe when it was only 380,000 years old. At that time, the universe was a hot, dense plasma, but it was starting to cool down. Because light travels at a fixed speed c, we know exactly how far energy could have traveled in those first 380,000 years. This gives us a standard ruler in the sky, a fixed size for the largest structures that could have existed at that time. In 1995, and again with the Planck satellite mission, astronomers pointed their most sensitive instruments at this ancient light. They weren't just looking for heat, they were looking for the size of the spots, or fluctuations in the radiation. Here is the trick. If the universe is flat, light travels in a straight line. Those spots should appear to us as being about 1 degree across in the sky. If the universe were closed, shaped like a sphere, the curved space would act like a magnifying glass. The light rays would bend toward each other as they traveled toward Earth, making the spots look larger than they actually are. If the universe were open, shaped like a saddle, space would act like a demagnifying lens, and the spots would look smaller. When the data came back, the answer was unambiguous. The spots were exactly the size predicted for a flat universe. This was a Galileo turning his telescope to the sky moment. It confirmed that our geometry is Euclidean to within a tiny margin of error, about 0.4%. This means that space on the largest scales is essentially a perfectly flat stage. But this brings us back to the original problem. How did it get that way? If the universe is flat today, it must have been born with a curvature of practically 0. In science, whenever you find a number that is almost exactly 0, it usually means there is a physical law or mechanism forcing it to be that way. Nature doesn't usually do almost by accident. This led physicists to a radical idea called cosmic inflation. Inflation is the ultimate fix-it tool for cosmology. Proposed in the early 1980s, this theory suggests that in the very first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. This wasn't just space getting a little bigger, it was space stretching by a factor of 10 taken to the 26th power, or more in less than a billionth of a billionth of a billionth of a second. This rapid expansion happened much faster than the speed of light. Now remember, Einstein said nothing can move through space faster than light, but there is no rule saying space itself can't stretch as fast as it wants. To visualize how inflation makes the universe flat, imagine a balloon that is all wrinkled and curved. If you blow that balloon up until it's the size of the sun, the surface where you're standing will look perfectly flat. You wouldn't be able to see the curvature anymore because it has been stretched out over such an immense distance. Inflation took whatever mess, curvature, or clumpiness the early universe had and ironed it out. It stretched the fabric of space-time so much that any initial curves became essentially 0 within our observable horizon. This solves the horizon problem too. Ask yourself, how can two parts of the sky on opposite sides of the universe look exactly the same temperature if they are too far apart for light to have ever traveled between them? In a normal Big Bang, they shouldn't be able to communicate. But with inflation, those two parts were originally touching. They were part of the same tiny, uniform nugget of energy that achieved thermal equilibrium before being ripped apart by the sudden burst of expansion. Inflation ensured that the universe was not only flat but also incredibly smooth. This is where it gets truly weird. Inflation predicts that the universe should be so flat that we might never be able to measure even the slightest hint of curvature. It pushes the boundaries of our observable universe so far out that what we see is just a tiny, microscopic fraction of the real universe. For all we know, the universe could be a giant sphere that is quintillions of light-years wide. But because we only see a 93 billion light-year chunk of it, it looks flat to us. It's like standing in a vast desert and assuming the whole Earth is flat because you can only see to the horizon. But whether the universe is truly flat or just appears flat because of inflation, the result for our physics is the same. It dictates how everything in the cosmos behaves, from the smallest atom to the largest galaxy cluster. What would change if the universe weren't flat? It sounds like a math problem, but it's actually a survival problem. The geometry of the universe is tied to the total amount of energy and matter it contains. This balance is what allowed the universe to live for 13.8 billion years. If the universe had been born closed, high density, gravity would have been so powerful that the universe would have reached its maximum size and then collapsed back into a singularity billions of years ago. There would have been no time for stars like our Sun to form, or for life to evolve over billions of years. If the universe had been born open, low density, the expansion would have been so dominant that matter would have been spread too thin to ever clump together. Imagine a universe with no stars, no planets, and no heavy elements like the carbon in your DNA. It would just be an ever-expanding fog of hydrogen and helium gas, getting colder and darker forever. Flatness is the only geometry that allows the universe to expand slowly enough for gravity to build galaxies, yet fast enough to avoid an immediate collapse. This just right density also affects how we see light. In a curved universe, our telescopes would give us a distorted view of the past. Gravitational lensing already does this on a local scale. When we look at a massive galaxy cluster, its gravity acts like a giant lens, bending the light from even more distant galaxies into arcs and streaks. This is how we mapped dark matter, by watching how it warps the light passing through it. If the entire universe were curved, every image we have of the distant cosmos would be magnified or distorted, making it nearly impossible to calculate distances accurately. By measuring the flatness of space, we are measuring the total energy budget of the cosmos. And when we added up all the stars, gas and dust we could see, the numbers didn't match. There wasn't enough normal matter to make the universe flat. This discrepancy is what led us to discover dark matter and dark energy. Normal matter, the stuff we are made of, only accounts for about 5% of the universe. Dark matter makes up another 27%. But to make the universe as flat as we see it, there had to be something else, a repulsive force pushing the universe apart. That's dark energy, which makes up a staggering 68% of everything. The flatness of the universe is the ultimate proof that the vast majority of our reality is made of things we can't even see. Because the universe is flat, we can predict its ultimate fate. In a flat geometry, the expansion will never stop. In fact, because of dark energy, that expansion is actually accelerating. This leads to a scenario that astronomers call the Big Freeze, or heat death. Over the next trillions of years, galaxies will drift further and further apart until they are no longer visible to each other. Stars will run out of fuel and die. Low-mass stars like red dwarfs will live the longest, up to 10 trillion years, but eventually even they will fade away. What's left will be stellar remnants, white dwarfs, neutron stars, and black holes. White dwarfs are incredibly hot when they form, but they have no new energy source. They will slowly cool down over trillions of years until they become cold, dark black dwarfs. In a flat, expanding universe, even black holes aren't forever. Stephen Hawking showed that black holes slowly leak radiation, a process called Hawking radiation. This means that over truly mind-boggling timescales, 10 to the 67th power years or more, black holes will gradually evaporate and disappear. Once the last black hole has vanished, the universe will be nothing but a sea of low-energy photons and particles, reaching a state of maximum entropy. Because the geometry is flat, there is no reset button. There is no big crunch to start a new Big Bang. The universe just keeps getting colder, darker, and emptier forever. This sounds depressing, but it's actually a testament to the stability of our universe. A flat universe is a long-lived universe. It provided the billions of years needed for the first stars to forge heavy elements, for planets to form in stable orbits, and for life to emerge and start asking these big questions. If the universe had any other geometry, we likely wouldn't exist. The weirdness of flatness is the very thing that makes our existence possible. The fact that we can even measure this, that a collection of atoms on a small rocky planet can determine the geometric curvature of the entire cosmos, is perhaps the most remarkable thing of all. We started as unaware things and became aware enough to map the history of time and space. But there is one more mystery that the flat universe presents. If everything began everywhere at once and there is no center to this expansion, how does that change our view of where we come from? We know the universe has a beginning, but the idea of a starting point in space is one of the most common misconceptions in astronomy. We've traveled from the smallest atoms to the largest possible geometry, and we've seen that the universe is a place of unbelievable precision. The flatness of space is a clue left behind from a time when the universe was smaller than an atom. It tells us that we live in a reality that was shaped by a sudden, violent burst of expansion that smoothed out the rough edges of creation. Think about the fine-tuning we discussed. The universe is like a high-performance engine. If any of its parts were even slightly out of alignment, the whole thing would have seized up long ago. The fact that it is flat means it is tuned for longevity. It means we have a future that stretches out for trillions of years, giving us plenty of time to explore the stars and galaxies that are still within our reach. But don't forget the dark side of this discovery. Flatness required dark energy, and dark energy is what is currently ripping the universe apart, ensuring that one day the night sky will be truly empty. The very force that made the universe flat and stable is the same force that will eventually end it. It's a beautiful, tragic balance. As we continue to send probes like Voyager into interstellar space and launch new telescopes like the James Webb and the upcoming Athena X-ray Observatory, we are constantly refining our map of this flat stage. We are learning that the invisible universe, the part made of dark matter and dark energy, is actually the part that's in charge. We are just the actors on a stage that is much bigger, flatter, and weirder than we ever imagined. If you want to understand space like a NASA-level analyst, quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. So next time you look up at the stars, remember that those points of light are following the rules of a geometry that was set in stone 13.8 billion years ago. The lines between them are straight because a force of nature ironed out the curves before the stars were even born. We live in a flat universe, and while that might seem simple, it is the most complex and improbable thing about our entire existence. But if the universe is flat and expanding everywhere at once, it raises a question that confuses almost everyone. Where did it actually start? If you can't point to a center, how can it have a beginning? This is the ultimate cosmic brain teaser, if you're ready to have your mind blown by the logic of a universe with a start but no middle. Click here to why the universe has a beginning but not a center video.